So here's the second drag integral we're going to do. Really common situation, free falling from rest, linear drag force going up. I'm going to use down as positive because it makes the signs easier when dealing with the drag, since that v is actually a vector velocity. So I always put the v in, or the positive in the direction of v. So first thing we can figure out about this really easily is that at terminal velocity, F net is 0, so the terminal velocity must be mg over b. Second thing we can do is draw the graphs. So we start off at 0 velocity, and we're going to increase until we approach asymptotically our terminal velocity, which is that mg over b. Which means our x graph starts off, since we start off with 0 velocity, we start off with a flat tangent. So a flat tangent line, and then it gets steeper and steeper and steeper until it approaches some limiting slope. So it asymptotically approaches a line. Our acceleration started off fairly big. Started off at g, actually, and then decreases until it approaches 0. So that's what we'll expect our function to do as well. Okay, so we're going to do separation of variables. We're going to get the v's on the right and the not v's on the left. This is a little bit harder because there's this function added in here, but I still do want to get v sort of as by itself as I can. So I'm going to factor out a negative b. And I'm going to take the dt and the m over to the left and bring this bit with the v to the right. I can't get the v all by itself, but I can get, I'll go as close as I can. Minus b dt over m, that's always something that comes up in these integrals. dv over. Okay, now I'm going to integrate and be careful about my limits. I'm going from 0 to t, and that takes me from my vi, which is in this case 0, to my vf, which depends on the t, so I'm going to call it v of t. So I'm solving for actually really a function. Alright, left side's easy enough. Minus bt over m, evaluated from 0 to t. Right side is a natural log. Just because this stuff is added there doesn't make it not a natural log, but nothing's multiplied, so we don't have to worry about any chain rule. So natural log of v minus mg over b. And we do have to evaluate from 0 to v of t. So this is the one that can get you. The left side evaluation is easy enough because the 0 term goes away, but the other one does not. So natural log of v of t minus mg over b minus the natural log of negative mg over b. I like to put this over to the other side. And now I exponentiate both sides. The right side's easy enough. We're just undoing the natural log. The right side, these two are multiplied together since their logs are added together, or since those two terms are added together. So that's just minus mg over b, and that's e to the minus bt over m. Put this over there, and I'm going to factor. So I get v of t is mg over b times 1 that I brought over here, minus e to the minus bt over m. Let's make sure that does the right stuff. So at time equals 0, this term is 1, so this whole thing goes to 0, which is what we wanted. As time goes by, this gets closer and closer to 0, which means that this function gets closer and closer to mg over b, which is the terminal velocity, so that is exactly what we want. Okay, if we want to do the integration to find the position, we need to rewrite that as dx dt equals this. And again, x doesn't show up explicitly, so it's an easier integral to do. Just bring the dt over and integrate. So integrate from 0 to x of t on the x side. Integrate from 0 to t. our function here, mg over b times 1 minus e to the minus bt over m. That dt is still over there, or is over there because I moved it over. Left side is easy, x of t. Right side, I'm going to think of this as doing it in two terms. So mg over b times t. Maybe I'll just leave this out. Times t. And the integral of this is negative m over b e to the negative bt over m. So this negative negative is going to make it a positive m over b e to the negative bt over m. And I do need to evaluate that from 0 to t. This term doesn't really do anything, but this term will matter. So mg over b times t minus 0 plus m over b e to the minus bt over m minus m over b times e to the 0, which is 1. So that's just minus m over b. I'm going to multiply this all out and see if I can I want to see if we can get this a little nicer. Maybe we can't get it too much nicer. So we have mg over b. I'm just going to group in here. T plus m over b times e to the minus bt over m minus 1. So what's going on here is that at 0, this term is 1, which means this whole thing goes away. This is also 0, so our initial position is 0. That's fine. As we go up, this term gets smaller and smaller and smaller. So we end up getting to a constant here. This goes to 0, so we get a minus m over b. But this term keeps growing, and so what we get is a line with a slope of mg over b, which is terminal velocity. So this slope is the terminal velocity, and it has intercept minus m over b times mg over b. So that would be, if I trace all the way down here, down the x-axis here. So that would be our intercept there. So this one grows without bound. It doesn't have an asymptote in terms of the position, but it does approach a line.